This is Kosmographia, the Randall Carlson podcast. And welcome back, ladies and gentlemen, to the Kosmographia podcast with Randall Carlson. What's up, Randall?
What's up? Well,
yeah, here you go.
Should we talk a little bit more about Atlantis, since that's what we've been talking about the last 3 or 4 episodes, before we move on to other things, even though those other things are, of course, related. It's all interrelated. Let's always keep that in mind.
100%.
So, yeah. Brad was talking a bit about the hurricane. I haven't had even a chance to check today to see what the damage is, but I understand it's pretty severe.
Well, yeah, just the west end of the Bahamas. It just sat there for, hours and hours with those winds at 160 miles an hour. So really devastated.
I heard that a hurricane, in terms of the energy of a hurricane, it can release the same amount of energy as a nuclear bomb every minute.
Yeah. It's pretty intense.
That's serious.
That's a lot of energy.
It's believable.
So you guys living out there in West Texas, you ever been in a tornado or a major cyclonic storm?
We came close. Harvey came really close to us.
Oh, I guess it would have, huh?
But we weren't affected because we're actually on a raised plateau, and we have like all these eroded hills, and so that it tends to break up serious storm systems pretty quickly. So yeah, we get tiny little storm cells, but we've never had some like massive. I mean, we get floods sometimes, I guess, but no hurricanes or tornadoes.
No hurricanes or tornadoes. How about that?
Yeah. Every once in a while we get a flood though.
Yeah.
Yeah, and those are real bad.
Yeah.
So what river watershed are you in?
I don't know. It's called the Edwards Aquifer. That's considered part of this gigantic aquifer or whatever. But it's all limestone.
So it's porous.
Very porous, yes. But it'll get saturated quickly, and then the water just raises enormously, and then we have flash floods and.
I see.
We have large, I guess you would say very large creeks. Like the Medina is a big one, or Guadalupe or whatever, and they're normally say 40 feet across and 5 feet deep, but they very quickly become enormous. And they flood entire towns and wash out. They'll carry buildings away and cars and trees and whole enormous amounts of destruction. So,
yeah, moving water is pretty powerful.
Yes.
It's right. Yeah, where I grew up, we were on the edge of Tornado Alley, so we had some close calls on several occasions. And then also being on the eastern side of the prairie, we basically had 500 miles between us and the Rocky Mountain front, maybe more than that, 700 miles to the Rocky Mountain front. So you have these air masses coming down, and they sometimes just pick up velocity over the prairie, and by the time they got to us, they'd be some pretty intense. So what's the strongest wind you've ever been in? Do you have any idea?
Well, I mean, we did go through a hurricane in Houston, just not where we live, but we were in Houston, and a hurricane came through, and I would say, I don't know, that was 110, something like that. It blew. Boats were going through the air, and it was blowing bricks off of people's houses, like actually dislodging bricks, and hurling them and all that kind of stuff. So yeah, we were young, but that was probably the strongest wind. Yeah,
when you get up, I think the strongest I've ever been in is between 80 and 90 somewhere, and it wasn't a tornado, it was a cyclonic storm. Where were we?
Atlantis.
Oh, Atlantis. Yes, Atlantis.
The dreaded A word.
The dreaded A word. The word which, as soon as you say that word, there's a certain subsegment of people that will immediately turn it off and run away.
Right. And another sub-segment that pulls out all their crystals and starts.
Yeah, right. That's the other subs. Right. So you've got those two. And basically what we should do is just put all of them in a room together, and they could basically just fight it out amongst themselves. Yeah, I've noticed sometimes people, when they have this false sense of rational superiority or superior rationality, they imagine that they're being, superior to people who would even consider such things as Atlantis, because we know that that's the ultimate tinfoil hat, right?
Right, yeah.
But I think if you've been listening for the last 4 podcasts, you'll begin to see that there's a little bit more to it, and that you have to actually look at it. You do have to look at it from a scholarly level. And it's just too bad that it has gotten that association with the tinfoil hat mindset, because that's kind of scared scholars away, or the people who could do serious scholarship are not doing it. So it's kind of left up to the mavericks and the fringe. And I would consider myself on the fringe, only partly because I try to keep a foot in both worlds, because you see, I think it was T.C. Chamberlain, one of the important, I would say, founding fathers of modern geology, who mostly was active late 19th, early 20th century. And he was the one who chastised his colleagues for being too prosaic, too pedestrian in their thinking, too limited. And he actually wrote a quite extensively quoted paper entitled something like "The Value of the Outrageous Hypothesis," and basically saying, you have to be able to sometimes think outrageously, because really, when you begin to look at nature and you look at the way things function, it is kind of outrageous.
That's right.
I mean, it's outrageous that I'm sitting here in Decatur, Georgia, and you guys are sitting there in Texas, and Brad is sitting up there in North Carolina, and we're all sitting here having this conversation. And why can we do that? When you think about the technology behind this, the last, without 200 or 300 years, really going back to the Renaissance times, this accumulated curve, this arc of learning that we've been, this ascending arc of learning that we've been in since the Renaissance, has basically led to us being able to sit here and do this.
Right.
And again, you can't understand that without understanding it within the larger context of the natural environment, the global environment, the changing environment, because it is changing, and it requires constant adaptation. And that's the thing. I think there's people out there now that are imagining there's some stability, some stable state that we're supposed to try to achieve. And once we get that stable state, we can kick back, and there's not going to be any more extreme weather or great tremendous hurricanes or fires or droughts or any of the other stuff that's been quite normal throughout the history of the earth. But so here's the challenge: define to me, tell me, when was that stable state that mythical stable state that we're trying to return to?
Right.
That's a question that needs to be asked of those who believe that there is some optimum state that we can get to. Now, I can imagine an optimum state, and I don't think it's anything that we've been in the last 200 or 300 years, to tell you the truth. And in fact, if we go back 7,000 or 8,000 years, there was a period of climate that the climatologists, the paleoclimatologists, referred to as the hypsothermal, but it was originally referred to as the climatic optimum.
Yeah.
See, and guess what? It was about 1 degree or 2 warmer than the planet is today. So that's interesting. So, and it's also interesting that the terminology shifted at about the time global warming became a political issue, when the terminology went from the climatic optimum, which carries a very definite implication, to the hypsothermal. Because when you think hypsothermal, that doesn't necessarily invoke the same idea, the same picture of a benign climate as the climatic optimum.
Right. Right. And that the climatic optimum takes place right after or close to within a couple of thousand years of enormous cataclysms in the climate, right?
Yes, that's exactly right.
Right. And so since we're talking about Atlantis, are we thinking that this civilization was in the climatic optimum or previous to it, do you think?
Previous.
Okay, previous to it.
Previous to it, yes. The climatic. Yeah, climatic.
Okay.
Climactic would be like the climax of something, right?
Okay.
Climatic. Yes, the climatic optimum. It didn't start everywhere simultaneously around the world. It was at various places in varying strengths, but you could say that between 9 and 10,000 years, and seemed to be pretty much well in place by 8,000 years. It lasted 2 to 3,000 years. It didn't end all in the same place. Some places began to cool off sooner than other places. But you had the climatic optimum give way to the neoglacial period. The neoglacial or new glacial period was generally a deterioration of climate that started in place about the mid-Holocene, which is, say, around 5,000 years ago, 5 to 6,000 years ago. And it affected the planet differently, depending on where you were. But it was generally overall a deterioration of the global climate from the warmth of the climatic optimum into the neoglacial period, which culminated in the Little Ice Age. And the Little Ice Age that ran from, say, 13 to 1400, again, it didn't appear uniformly everywhere all at once. And in some places were barely affected by the Little Ice Age, but there is certainly enough evidence to demonstrate that it was global overall. But so between 13 and 1400 is when you had a corresponding deterioration of climate that began after the medieval warm period, which of course is the time when the Vikings were colonizing and farming West Greenland. And it's generally considered that the climate was around a degree and a half warmer on average. In some places, maybe more. In other places, maybe not much difference at all. But overall, there was a general increase in warmth from about 900 to 1200, right in there. That, as we've talked about, coincides exactly with the a human population expansion, a considerable, significant human population expansion, only because the growing season got longer and there was more rainfall in a lot of places, particularly in Europe, and that abundant rainfall and longer growing season allowed for abundant harvests. And successive years of abundant harvests created a lot of food for people to eat, and people started living longer, getting bigger. We see actually an increase in human stature throughout the medieval warm period. And then there was enough, the population grew, and after a century or so of the medieval warm period in Europe, the population had grown where you could now create enough of a surplus that you could develop these armies of craftsmen that were necessary to execute this great enterprise of cathedral building. And that lasted until pretty much what you see is the end of the medieval warm period, which was probably triggered by a couple of back-to-back big volcanic eruptions in the late 1200s and then again in the early 1300s. So what happened was you had the return of the first phases of the Little Ice Age, which brought in cold, and there was a succession of bad years, of cold, damp years in the early 1300s that led to a whole sequence of crop failures, which in turn led to famine, which in turn led to people declining in health. Their immune systems got weak, their resistance to disease. And then in the 1340s, you had the bubonic plague that was able to, the opportunistic disease that swept over Europe. And of course, once you had a third the population wiped out and the rest of the third just trying to do what they can to survive, you're not building cathedrals anymore. So that was kind of the end of it. That was the end of that. And that's why a lot of the cathedrals basically from the high Middle Ages never got finished, was because of this deterioration of climate. Now, so then what happened is we have the Little Ice Age with varying decades of intensity that lasted until about the mid-19th century. And then it began to ameliorate, and it began to steadily warm up. The planet began to steadily warm up, and it's been warming up uniformly for about 150 to 170 years. And this is easily demonstrated. We see that the glaciers worldwide during the Little Ice Age, they grew to the largest extent, mostly around the world, that they had been since the end of the Great Ice Age. So it's important, that's an important thing that to a context in which to place your thinking about when you start talking about glacier recession, is that the glacier recession started from this massive expansion of the glaciers that took place in the Little Ice Age. The Little Ice Age, in turn, was the culmination of this whole deterioration of climate that began between 5,000 and 6,000 years ago that was called the neoglaciation, that came in the wake of the climatic optimum, which, after, like what you said, came almost immediately after, on the heels of a whole succession of these massive catastrophic changes. And it's those catastrophic changes, this 3,000-year episode, roughly lasting from 11,500 to about 14,500 years ago, it's within that context that we have to place the story of Atlantis, if there's any veracity to the story at all. And so Plato, as we discussed, he gives the date. He provides us with enough information to deduce a date, which would be about 11,500 or 11,600 years ago, because he places it at 9,000 years prior to Solon's journey to Egypt, his exile, 10-year exile, where he went to Egypt, and then, according to his story, which he then passed on, that over through 5 iterations reached Plato through Socrates. He recounted the tale of Atlantis and placed the priests placed the tale of Atlantis as occurring 9,000 years earlier. So if we know that Solon's exile to Egypt took place, and Kyle, maybe you could look it up and give us some exact dates on that. And then if we extrapolate backwards 9,000 years from that, we're interestingly going to get, coincidentally, the beginning of the Holocene.
Yeah, so I have a quick question about that, because in Plato's dialogues, the Egyptian priest is telling Solon that their records, they remember like 5 or 6 destructions of the world.
Yes.
So what do you think about that? Is he talking about previous? I mean, like, it doesn't necessarily mention civilizations in those destructions, like, but right. He said, remember, which implies if you have like records, then there was some kind of civilization keeping a record that continued on through those destructions.
Exactly. And I will pull up a slide here, and we'll do a screen share. All
right, great. And Kyle's looking up those dates too.
And while you're looking at that, if people coming into this episode new, they want to go back to episode 3, which we really get into the Atlantis basics through episodes 3, 4, 5. So if they're coming in fresh, they ought to go back to the start of this discussion from episode 3.
Yeah, that's absolutely right.
So right. I don't know what you're getting at. I don't want to jump in front of there again. So I won't list off any of the catastrophes or floods that they could be talking about, those 5 or 6. So I'll let him go, not knowing what he's going to pull up here right now.
You can't say that and then not give us those catastrophes.
Well, I think he's about to lay him out.
All right.
Yeah, I'm gonna have to read this whole Wikipedia page, which is fine. But it did not immediately tell me.
Okay, well, that's okay. I'll just look at some stuff here, and I've prepared a graph. I don't think I have shown this graph yet. I think this might be the first time, so let me do a share.
Yep, we see that.
Okay. Oxygen isotope ratios from Greenland ice cores, from which we can do a pretty accurate reconstruction of paleoclimate. And what we can do here is this is, if you go down on the right-hand column, you'll see years before present. And at the bottom, you've got 10,000 years before present. And you're coming up, there's your various dates. And you'll see at the very bottom, you've got shifting to the left is colder, shifting to the right is warmer. And if we go down the column here, these are the relative oxygen isotope ratios, which we'll explain sometime. I'm not going to get into the background of that tonight, but at another recording, we can delve into some of the specifics of these dating processes and other proxies for, and that's what this is. This is a proxy for global temperature change, because what it does, it's the cooling and the warming changes the concentrations of the oxygen 18 ratios that are preserved in these ice cores. And the ratios between oxygen 18 and oxygen 16 in a variety of settings will fluctuate according to temperatures. So that's basically what we're seeing here. And if we start at the top, we're at the present. And if we go down this column over here on the left, the Holocene interglacial, I'm calling it 10,000 years, just simply in round numbers, although in virtually all the literature now, the Holocene is marked as beginning at 11,600 years ago. So going backwards down, we have the Little Ice Age, and you'll see that there's two phases. And there was a warming phase sort of that broke. And if you look at the graph here, you'll notice if the graph peaks to the right, it's getting warmer. If it peaks to the left, it's getting colder. So what I've done here is this vertical line represents the modern temperature for comparison. So you can see that the temperature is waving back and forth across the modern average, right? I think you would say that this line would probably represent the average between, say, 1950 and maybe 2010 or so, when this graph was first published. Actually, no, about 2000. So that period in there. So you'll see here, if you go down, you had the Little Ice Age was in two phases. A colder phase that began it, and then it was broken in the middle by a warmer phase, which, as it turns out, was pretty much the Renaissance, which could have been related to the fact that you had that little break in the cold. This period right here ended with a plague that wiped out huge percentage of Europe right here. So then you had, by the time Leonardo da Vinci came along in Florence, they were just recovering from the latest phase of the Black Plague.
What's the rough? I'm sorry. What's the rough? In degrees, those shifts, like 1 or 2 degrees or something. What's the?
Well, like taking this spike right here, that's about a 4-degree spike right there.
Okay, all right.
And there are some interesting spikes you look in here. So if we go down, you'll see that this orange represents the medieval warm period. And you can see that there's this stretch on the graph where most of the peaks are to the right, to the warmer side, right? And then you see the Dark Ages, you had a lot of variability in there. And quite a bit of that variability was shifted over to the left of that vertical line, which meant that it was a cold period. The Dark Ages were generally cold, that gave way to the medieval warm period here. Prior to the Dark Ages, you had what's called the Roman warm period. And you'll see that there's some strong, that the curve is strongly tilted over here to the right side. Even though there was a fair amount here to the left of it, to the right, it was most of this period is warmer than the line at present. Then you go back, there was a cold period right back here, a short-lived cold period that coincided with the Bronze Age collapse. Bronze Age collapse is something that we at some point we'll do an extended examination of that Bronze Age collapse, because it's a very important, very interesting phenomenon what happened at that particular time, because this seemed to be a catastrophic destruction of civilizations around the Mediterranean basin. So then you go back a little further and you get this warm spell right down here. Notice about 4,000 to 4,400 years right in here. You have almost nothing to the left of the line. You see that? And that coincides with the Pyramid Age and the Old Kingdom, Egypt, Sumer, and so on. Going back here, we have the Bronze Age. You'll see here that we're actually now getting back into the climatic optimum. And you see climatic optimum in two phases. The first one begins here at the very lowest, almost 10,000 years ago. And if you look at the very bottom of the graph, you'll see that it's coming up from the cold side. It's coming up and it crosses the bar. And for, geez, about the next 1,000 years, it doesn't go to the left of the bar at all. So that was the
close to the bar there.
Yeah. So that was the first phase of the climatic optimum. It was broken right here by this enormous spike of cold weather that lasted maybe a century or 2 centuries. So it had its share of trouble. But then you get over here, you see that the second phase isn't quite as warm as the first phase. But overall, it's highly weighted to the warmer side of the vertical bar. You see that there's almost nothing. There's little blips, little things there here and there, but most of it's weighted over here to the warm side before you get to the Bronze Age. And then in the Bronze Age, it's still fairly warm. And it's not really until you get up here, you'll notice, if you notice the trend, it's generally been getting from the climatic optimum to the Little Ice Age. You can see that it's been generally shifting predominantly to the cool side. That's pretty obvious when you look at it. Notice also that as you're shifting more to the cool side, notice that the amplitude is generally greater between the peaks of warm and the peaks and the troughs of cold, if you will, as compared to back right here. You'll notice the amplitude of the back and forth here is not as great as it is up here, is it? So
that's always kind of made sense to me, because I think of it in terms of like a warmer climate is a higher energy system, and a higher energy system is more likely to be stable, right? When you start dropping in energy, then it's easy. I think about just in terms of like, if I'm thinking about pressure, when you have a low pressure environment, it's easy to fluctuate the pressure back and forth. But if it's extremely high pressure, it's harder to make it fluctuate, right? So that's what I think in terms of that.
Well, that seems to make sense. So it's an interesting graph, and there's a lot to be gleaned from it with a lot of implications. One being that, the second half of the Holocene has not been as stable as the first half. And the second half of the Holocene also has generally been cooler than the first half of the Holocene. So, and then right down here, you'll see what's happening is it's shifting to the left. It cuts off just below 10,000 years ago. And I have another graph that I can pull up here. That's actually the same graph. It's just been stripped down and made much simpler. But here is that 8,200 year spike. It's basically the same data. It's just, their bar is put right here, and you can see, but it's the same idea. You can begin to look at the fluctuations, and here's the medieval warm period right there, and here's the Little Ice Age, this trough, and here's the present global warming. So actually, when you look at it in this context, the present warming doesn't really look all that warm. But what's interesting here is when you get back, you see the other graph that I just showed you where it's trailing off into the colder, that's this line right here. So what it does is it trails off and it drops way down here into the Younger-Dryas. And this is where the planet gets really cold after this huge spike of warming right here. Now, the dating of Atlantis basically is this right here. See that spike right there?
Oh, yeah.
It's coming all the way up, and then boom. That right there is the beginning of the Holocene, 11,600. And it's also the date that Plato gives for the subsidence of Atlantis. So now what's interesting is that that date coincides with one of the great meltwater pulses of the global oceans, which of course are related to the influx of glacial meltwater into the ocean basins of the world, which is in turn related to a warming of the climate or some type of an injection of enough energy into the global environment that it can trigger this massive melting of the 6 to 7 million cubic miles of glacial ice piled up on the continents. And now you start returning that water to the global oceans, you're going to get sea level rise. So you've got a whole succession of interlinked things here. You've got the sea level rise, which is the result of glacial melting. You've got the glacial melting, which is the result of this injection of energy into the system that wasn't there during the full glacial maximum. So the question that's raised is, what was the source of the energy necessary to raise the temperature of the Earth fast enough to cause these tremendous spikes of meltwater to gush off the continents and back into the ocean basins? And so there was over here where I'm tracing up, there was a huge meltwater spike right there at this warming. That was meltwater pulse 1A. It's generally dated around 14,500 to 14,600 years ago, which for now I'm prepared to accept, although I would look a little further that perhaps some of the events that were transpiring in this transition from full glacial, which is all the way over here to the left, up to interglacial, which is this Holocene graph right here, the inputs of energy that brought us from this stable, semi-stable state to this state up here may have contributed to contaminating the record. It may have contaminated the radiocarbon record. It may have contaminated the geomagnetic record. And the things that are now being used to determine these dates, they may have been biased for example, by a massive flux of radioactive carbon into the atmosphere. Perhaps some type of a response from the Earth's geomagnetic field that causes enough fluctuations that assumptions that are made about the timing between those fluctuations, which may actually be taking place much faster than some of the chronologies that are based upon other assumptions. So my point is that I would take this dating here, once you get past this point, because of the enormity of these changes, I say that what I'm saying is that we should be a little bit suspect about the dates. I would not be surprised if there were further refinements of those dates that took place. And what I'm getting at in a big roundabout way is, for now, I'm going to go 14,600 for this warming spike right here, which coincides with meltwater pulse 1A, which was the first really massive pulse of glacial meltwater back into the global ocean basins. Now, getting back to the subject of Atlantis, one of the things that I'm trying to suggest here is, when we strip all the woo away from it, if there was a place around the planet that might have been a benign place, an optimum place for any kind of an advanced civilization to have evolved, it could have been the Azores, the region of the Azores. And now I say advanced civilization, let me qualify that. I might be talking about something no more advanced than the Minoan civilization or the Phoenician civilization, one capable of carrying on fairly extensive maritime exploration, commerce. There could very well have been colonies. There could have been other communities 15,000 to 20,000 years ago that, essentially, once you've gone through this succession of changes to get from here to here, once you begin to understand the physical dimensions of those shifts, we're talking about things that basically completely remodeled most of the planetary surface. So once you understand that, then you're kind of more in a position to go, okay, well, there could have been, maybe not. And I'm not saying, a technology like our own today, that they're building cars and using fossil fuels and airplanes and television sets and all of that. An advanced civilization, there may be ways that an advanced civilization could evolve that we haven't even begun to imagine yet. And I think that's a very profound possibility. So what I'm getting at here is, let's strip away the woo, but let's just look at this also objectively and open-mindedly and consider that, yeah, there's nothing intrinsically impossible about there having been advanced maritime civilizations during the Ice Age. So if you got a problem with that, you probably should go somewhere else, because,
There's also
evidence
in the maps, right? Like, I don't know how much you've gone. Graham Hancock goes into this great detail.
The Peri-Rias map, the Orontius Phineas map. Yes.
Phineas, yes.
I mean, how do you explain that? It really does appear that somebody was able to accurately map large sections of the Earth's surface long before they were supposed to be able to do this. And these maps show Antarctica and coastlines of Antarctica and of South America, before Antarctica was discovered.
Right, and long before we were supposed to be able to do anything with longitude, really, right? They had the problem with longitude. It wasn't solved until we had accurate timepieces in like the late 1800s. So when you have these very accurate maps that seem to come from source maps that are incredibly ancient, that are now lost. The mathematical ability is just that implies, spherical trigonometry and stuff you have to know to be able to do that kind of cartography, implies at least a somewhat advanced civilization.
Their gear spring technology was top notch.
Okay, so let's take a broader look at this graph again, because this graph is so important. Basically, now what we're here, this is the entire graph going down to 250,000 years ago. And you can see that the top half of the graph, this is exactly what we were looking at before. There's the 10,000 years, and this is the Holocene right here. There's that 8,200-year cold snap right there. This is what we were just looking at. And then it veers down into the full depths of glacial cold, and then you can begin to see the difference. So if you want to talk about climate change, you can't talk meaningfully or realistically about climate change without addressing this that you see right here.
Yeah, those are enormous shifts in temperature.
Those are shifts that utterly dwarf anything we've seen in the last 200 years.
Yeah.
I mean, all you have to do is look at the magnitude of the graph here. Please, somebody explain this to me, right? At this point, there's nobody explaining that. So if there's nobody explaining this, which really was the norm for a couple of 100,000 years, then don't stand there and tell me with a straight face that the debate on climate change is over. But right in here, this is this peak, this after you have this major warming spike right here, which coincided with meltwater pulse 1b, then you'll notice you have this succession of lurches back into full glacial cold. And the depth of the full glacial cold right here coincides with that Younger-Dryas boundary at about 12,900 years, roughly. That's that spike right there, that spike of colder. And you can see basically what happened is that the climate lurched back into the full depths of glacial cold after warming. Now, notice that the trail here is you're coming from the full depths of the late glacial maximum, which is about right here at about 20,000 years ago. If you were to take this whole big massive convulsion out of it, you can see that this would sort of almost continue and tie in right here. You see that?
Yes.
Yeah. Right. Okay. Now, we talked about Milankovitch forces, which is the shifting relationship between the Earth and the Sun due to the distance between the Earth and the Sun at its particular season, the tilt of the Earth's axis, and so on. These Milankovitch forces are inducing climate change on a very long, protracted scale. So you've got slow changes that are accumulating over centuries. And if we go back to the end of the last ice age, we begin to see that after the full depths of the glacial cold, it began to warm. The climate began to warm gradually, and this was consistent with a greater influx of thermal energy to the Earth due to changes in the Milankovitch relations between the Earth and the Sun. So it started warming, and as a result of that initial warming, gradualistic warming, the great ice sheets began to contract. And once they began to contract, there was enormous amounts of augmented floodwaters coming off of the ice sheets, right? So there was an enhanced flux of glacial meltwater from the continents back into the oceans with this Milankovitch warming. But then what happens is that Milankovitch warming right here, like I said, using the present date at about 14,600 years, that Milankovitch warming is suddenly interrupted by this massive spike of 10 or 12 degrees centigrade warming. I mean, literally in a matter of a few years. Within less than 5 years, maybe as quick as a single year, right? So you've got now 10 to 12 degrees centigrade, it's going to be 18 to 20 degrees Fahrenheit, right? So that is an enormous spike of warming. I mean, it's 10 times beyond the warming we have seen in the last 150 years. So anyways, you've got this first enormous spike right here. Then you've got all of this lurching back and forth down to the depths of the Younger-Dryas right here. And then you've got the second warming spike coming out right here. And then whatever happens, the planet continues on out of the ice age and comes up into the climatic optimum right there.
Yeah.
And so it's interesting that almost immediately after this violent cataclysmic birth of the Holocene, nature almost went through this 3,000-year period of being very benign and almost nurturing, because think about survivors of this catastrophe. Now, bear in mind that it was between these two spikes that most of the great megafauna of the Pleistocene, of the late Pleistocene, disappeared. And it was also at the end of this right here, right in this area, where the Clovis culture disappeared, right? So are these unrelated? Is the disappearance of the Clovis culture and possibly the Natufians in Europe declining in numbers at the same time? The disappearance of the megafauna, half of the species, great megafaunal species of the planet, roughly disappearing within this window right here. I would say, yeah, there's definitely a correlation between that. I mean, how could there not be? Because look, we're talking now about species going extinct with another degree or two of warming in the next 100 years. And if you read some of the popular literature now that's designed primarily to get people worked up into a frenzy of fear about a minuscule change in climate, the fear is that, we're going to lose a tremendous number of species in the next century if the planet warms another degree or two. Well, here the planet warmed 10 degrees in 1 to 5 years, and guess what? You did have extinctions in there. And interestingly, a lot of these species that were able to survive through all of this,
that's what I was going to ask.
Didn't make it through there. So there was something qualitatively different about this Balling-Alarod Younger-Dryas pre-boreal transition, which is basically what you're looking at here. Balling-Alarod is this warming that you see right here. Then you have the spike, and then you have the Younger-Dryas, and then you have the pre-boreal coming out of the Younger-Dryas. And so by the time we're coming out of the Younger-Dryas, half the megafaunal species of planet Earth are gone.
Right. And you've said before that humans are a form of megafauna. So
yeah,
like that correlation of like Clovis people and other people's disappearing along with all these other, megafauna mammals makes sense, because humans are a form of megafauna. So yeah, if megafauna were dying, then so would humans be dying.
Well, yeah, it would make sense.
Yeah.
And so in the aftermath of these cataclysmic transitions here, basically what you had is, as you come into the climatic optimum, you had a rapid recovery of natural ecosystems, wide scale, right? And you had low population, and you had essentially no competition for space or resources. And so most likely when you begin to look at the broad scale of a global catastrophe, undoubtedly what you had was large areas of the planet that were essentially depopulated. Other places that would have been in ecological terms a refugium, a place of refuge where life was able to survive, where species were able to survive, where perhaps pockets of survivors who then were able to essentially begin to recover once the dust had settled. But what you would have would be in an environment like that, you would have isolated groups of survivors that are basically.
Imagine how long they could go. You know, how many of those groups would have assumed for one reason or another that they were the last people left on Earth. And you could go, and then they go thousands of years before it, and then suddenly they meet people and they're like, whoa, you know.
Exactly.
All of your oral traditions are telling you you're the only ones left. You know, I mean, that must have been nuts.
When you begin to appreciate the magnitude of the global changes that transpired during this, it makes perfect sense because geologically, we're going to go out and we'll begin to teach people how you can recognize these boundaries and how it becomes clear that, yes, huge swaths of the Earth's surface were completely erased. You know, when you're talking about erosional events always coincide with depositional events. And so one of the things that when you begin to look at the what I would call, let's say, cataclysmic geomorphology, you begin to see that there are places where large tracts of the Earth's surface have been stripped away, and other places where vast tracts of the Earth's surface have been buried, you see, because if you strip away from place A, it's going to bury place B, wherever it ends up, if it's not fully carried out to the ocean. But there are many places where, you know, you've got hundreds of feet of sediment that are essentially entombing the pre-existing landscape. And you've got other places where that pre-existing landscape is gone, completely gone. And you might be standing on the modern landscape, but the pre-existing landscape might have been hundreds of feet over your head. But that material is gone, see? So whatever was going on there culturally, there's not going to be any trace of it left. Conversely, if it's in a depositional environment, it's possible if that it was low energy enough that there could be things preserved. And I think that we're going to be finding some of that stuff buried, in some cases hundreds of feet under the present surface of the Earth. In other cases, you know, 200, 300, 400 feet below sea level. But bear in mind, when you have these huge meltwater pulses, you're going to talk about a very agitated ocean for a period of time. And as the ocean is rapidly rising like that, you're going to have very high energy typhoons. You're going to have storm surges. You're going to have just the wave action alone of this rapidly rising sea level is going to tend to be highly erosive to anything that was there on the previous coastline. Because when you go back to this period, say 15,000 years ago, you're looking at a coastline that's, you know, 400 feet lower than sea level. So it's going to be massively shifted in a lot of places from where the present coastline is.
Yeah, in some cases that's hundreds of miles, right?
In some cases, yes.
Yeah.
So that rising sea level, that highly energetic rapidly rising sea level is going to tend to erase those coastlines. So but even given that, I still will predict that we're going to begin finding more and more evidence once we get the technological capabilities to really explore archaeologically at those, you know, below sea level, that we're going to begin finding stuff that's showing, you know, what was going on there 5,000, 10,000, 15, 20,000 years ago.
Out at the edge of the continental shelf.
Right.
In a lot of cases, yes, it does coincide with the continental shelf.
One cool thing that people can do, I've done this with Google Earth, is you can look at some river systems that are coming off the landmass and going, just pouring into the ocean. If you're looking at Google Earth and looking to the sea bottom, you can see that the canyon that river is in continues way out under the ocean, which is only possible if that used to, you know, when that was dry land. So you can see the erosional features of the river continue out sometimes, you know, many, many dozens of miles beyond the present shoreline, showing you how the that the ocean has risen up over that canyon since those meltwater places. So
yes.
Excuse me, Mike. Randall, I didn't want to interrupt, but before you get away from that graph, I think you need to take a minute to tell people the source of that. If that's the Greenland Ice Sheet Project, it was the early 90s, so that data's been around for 25 plus years.
Yeah.
There was another Greenland Ice Sheet Project 2, I think, was the early 2000s. So this is something that's online and people can find, and it's been available for people to study. But yeah, if you could talk, a minute about what actually where that graph comes from.
Yeah, well, it was a 5-year project of extracting cores from the summit of the Greenland ice sheet. There was a European team and an American team. It was a very heroic enterprise. Again, they were limited, throughout the year. There was only a small window when they could actually get up there and drill these cores. So you got a picture, a core here that I'll go back to that graph, pull it up again. But you got to figure that there's a core here that's going down. No, let's see. Okay, so if we go down the left-hand side, you'll see 1,500. That's 1,500 meters, right? So 1,500 meters that's just under 5,000 feet. So that's almost a mile down right there. So you got a picture. You get an ice core that's maybe 5 inches or so in diameter. And the damn thing, it comes out in pieces, but the full extent of it, it's a mile of ice.
A mile long.
Yeah, because previous ice cores were taken closer to the periphery of the ice sheet, where there's more ice movement. So the idea of going to the summit was to try to get the most stable mass of ice, extract those cores, and then begin to analyze what's going on with those cores isotopically, what's going on in terms of gaseous inclusions, as you might find in air bubbles, and things like that. So the study of these ice cores is ongoing. And, there's a whole archive. I'm not sure where these ice cores are archived at right now, but they're there. And, if we get some serious scientists coming up that want to study this further, those ice cores are there, and they really deserve a lot more study than they're getting, because obviously if you're talking about 200,000 years of time, well, nobody's looked at all 200,000 layers of ice comprising that the whole column. I mean, there's a lot of work there that could be done yet to disclose more information. Because when we go into this graph and we go to this stage right here, bear in mind that you're looking at 12,000 years to 250,000 years compressed into this first 1,500 meters here. Actually, look, this shows the whole thing, which goes down to 3,000 meters, right? So that's the full depth. So when you get down to 3,000 meters of ice core, so I was way too conservative before. So 3,000 meters is right at almost 10,000 feet. So when you go down through 10,000 feet of ice, you're now to the from the summit of Greenland. You're now at basically base level, and you start bringing up rocks and soil and things.
Yeah, Mike, did you have a question before we move on to the next? You were going to ask something.
No, I was just going to comment with your remark about the canyons. Those would be the most likely places to look for civilization, evidence of civilization.
Yeah.
In underwater archaeology, because that's where people live.
Next to the rivers.
Except Mike, except that those canyons are massive meltwater conduits. The force of the water flowing through those canyons would have been enormous. So part of my point is that, yes, and in fact, it's true whether you're looking at submarine canyons or if you're looking at river valleys above sea level. Almost all of the rivers you can look at one point carry these enormously augmented flows that would have essentially wiped away anything that had existed there. Villages or communities or even towns or cities, you know. Some of the early towns like Jericho and Katolhoyak. Let me see if I used to know how to say it.
Yeah, Çatalhöyük or something like that.
Çatalhöyük, yes.
Çatalhöyük, yeah.
Yes, are between 8,000 and 9,000 years old. Now, there's no reason we couldn't say such an urban area couldn't have existed 15,000 years ago. I mean, that's just an assumption. But the thing is that a city like either one of those existing in any river valley is not going to survive these transitions that we've just been looking at here. I'm going to pull up some interesting graph here to further try to.
Well, I was going to ask about that too. That, you know, if this period where the sea levels were 400 feet lower, you know, there's going to be isostatically, there's going to be a completely different situation in terms of elevation on the ground.
Oh, yeah.
Right. I mean, how do we know that those continental shelves weren't actually much higher than they are now? Because you would have had these huge ice caps sitting on the ground, pushing down in different areas than where the ocean water is now pushing down, etc.
Well, one of the things now that's been well documented is the presence around the great ice sheets of what is called the Glacial Bulge, because as you push down here, it's like the rim rises up. So you've got around the periphery of the ice sheets, you have tremendous vertical movements. Under the ice sheet itself, it's pushing down, but around the rim, the response is to bulge up. So then when the ice is removed under that, in this basin, it begins to rise while the forebulge begins to drop back down. So yes, that's one of the important points here, is that, you know, for nearly 100 years, going on maybe 80 or 90 years, the idea has been out there of lateral motions of the Earth's plates. Since about the 1960s, continental drift has been an accepted part of, you know, geological activity, right? Geophysical activity of the Earth. But I think what's been underappreciated is the possibility of the vertical motions. And that's what we were talking about in previous podcasts. And it's very possible that some of these vertical motions were considerable. I mean, hundreds, if not even 1,000 or more feet. So that being plausible, if there's any kind of a scientific explanation at all for the idea of a subsiding landmass within an ocean basin, it would be the isostatic changes, the isostatic adjustments of the Earth's crust due to glacial loading and unloading. And so to set the context, we're looking at this, you're seeing this image right now, right, of the present coastlines.
We see it.
Yeah. And so we're going to toggle back and forth between now and, say, late glacial maximum, 15 to 18,000 years ago. So when you do this, you know, and if you look very carefully, you will see, I'll just say, look down here at the peninsula of Florida, what happens when I toggle. You see Florida itself is about double the width.
Oh, yeah.
You see that?
That is awesome. That is
yeah.
Great.
Yeah, and you look at the islands down here, Cuba, you could almost swim from Florida to the islands that are now much, much smaller. And so again, this would have been a place where you could have had an emergent civilization. You could have had
what's the thing in the middle of the Atlantic Ocean right there?
Oh, I don't know. What is that? Could it be the Azores Plateau?
I think it might be.
Okay.